Well, guys, in today's video, we'll be working on a mocap system from scratch. The thing here is to actually build a low-cost motion capture system, which means that we don't really want to use very sophisticated equipment, for example, very expensive cameras or any kind of equipment which are generally used into these kind of systems. So our main challenge is to only use this hardware, which is basically an RGB Amazon camera. It has nothing special. It was very cheap, and well, the thing here is to only use this for building our system. Despite this, we're going to use different technologies that are already built for us, such as MediaPipe. But now, why working with MediaPipe? I think that it's because it's one of the most reliable algorithms available for free. If you have some experience working with these traditional computer vision algorithms, you probably know that you can have the best filtering process, the most efficient algorithm to compute different kind of mathematical expressions. But if you don't have a really good detection system, it simply won't work. So this algorithm from MediaPipe is pretty reliable, and most of the times it works. It doesn't have like false detections, and of course, it's really, really easy to use. So this is the main reason. MediaPipe also already offers what we need, but what I want to say is that everything it's done for us, and the process gets really easy. So let me show you the output that we're gonna get. So let's open our terminal here, and at the end, this is where we're gonna get. As you can see, this is a 3D pose human detection. The main reason why I wanted to do this video is because this process combines a lot of topics, a lot of concepts that I think that they're really interesting, and sometimes they are kind of hard to understand. But I think that this is a very practical way in which we can integrate this kind of different concepts and mathematical process that are not really friendly to learn by ourselves. So I hope that you can enjoy this as much as I did. So what I'm talking about is that we're gonna be using first of all, the most important thing, and it's solvePnP method from OpenCV. It's very easy to use because, as I already said, MediaPipe already outputs what we need. Another thing, it's about the camera calibration. If you ever have heard about this, I think that it's a really important concept because if you were working with 3D computer vision algorithms, you probably know that working with depth information is one of the most common problems. But with camera calibration, everything gets easier. So don't worry about that. We'll explain it later. And of course, working with this demands working with a lot of matrix transformations, particularly with homogeneous transformation matrix. So take this into account. If you have no idea what this means, I really recommend to stop the video and just give a quick review about what is a transformation matrix. With this, I think that it's pretty simple, and don't worry if you don't understand, we will discuss this during the video. So again, so here's the code, guys. Yeah, as I already said, it's a really basic code. It has nothing special to be honest, but I think that it's still very interesting to integrate all of these concepts. The only thing that you should know about MediaPipe is that it outputs two different, for us, we'll be interested in getting two different outputs from MediaPipe, which are basically the image landmarks and the world landmarks. As we already know, the image landmarks represents only a two-dimensional array, which are XY coordinates from a pixel, from the image pixels. So there's nothing special with that. And on the other hand, the world landmarks from MediaPipe. It's really, really important for us to understand that we cannot work directly with these landmarks into our motion capture system. This is because they're normalized into inner process. For example, its origin are on the hips, so we cannot work directly with that. And why using the camera calibration? Because with this, we can work in the same reference systems as Unity works, because all these transformations on the feature will be transmitted to an Unity avatar, so the avatar can actually do in real time what we're doing with our camera. So as you could see on the plotting, the region was a blue dot, which represents the camera. So it means that the camera it's literally on 000. And for example, if you place your camera on 000 and you place yourself on like 3 meters away from the camera, the plotting will represent this. Will represent exactly this. And with this information, we don't have to actually deal with that mistakes or information. So this is the main advantage again. So I hope that I explained myself correctly. So the next thing here is to work with the global pose function. As I already said, solvePnP will be the root of this process. Where with this method, what actually does it's to I prepared this. What is solvePnP, first of all? I know that there are a lot of videos on YouTube available on YouTube that explain this a lot way better than me. But I just want to say that this method helps us to get the orientation and position, which is basically the 3D pose of the human in this case, from an object to an RGB camera system. What we explained before. This inputs the dimension or coordinates, which what we already have, and with camera calibration info. Again, I know that there are a lot of videos or available information on the internet explaining how this camera calibration works. But anyway, I'll be posting on my GitHub repository a code to actually do this calibration. But what is the camera calibration? This will help us to get our camera system into a metric reference, for example. And this outputs basically two different things, which are very, very important, which is the camera metrics that basically contains the intrinsic parameters like the focal length and optical center. The other thing is the distortion coefficients, which are basically a motor radial and tangential lens distortion. Don't worry if you don't really understand what this means. The only thing that you have to know is that this helps us to create a metric system from the camera. Well, literally, that's everything you have to know for now. The next thing, these 2 and 3 steps are part of the transformation, which is basically this method. But I think that there are some things that you should consider. First of all, we have those construction. We're loading the camera calibration parameters from an MPC file. We're extracting this data, the metrics, and the distortion coefficients. And these arrays, I know that this looks a little bit ugly, but the future will make this look better. These arrays basically represent the landmarks in specific order in order to represent every part of the body, such as the head. The head, for example, is represented by the 8th, 6th, the 6th, and the 3rd, and etc. The landmarks from MediaPipe. And these arrays at the end are built into another full body array, which relates every part of the body, so that we can actually plot this in a very simple way. So this is the main reason why this is here. What is a landmark? I'm sorry, but this image represents basically what is a landmark. There are 33 landmarks for MediaPipe, and the same are for the image and world coordinates. So don't worry, there's nothing more about it. So this is what actually matters from this code. This is the most important thing, which basically applies the transformation to our coordinates. As I already said, the output for MediaPipe is actually our landmarks array, which it's normalized into the MediaPipe inner system. What we want to do is actually apply this transformation. solvePnP returns T vector and R vector, which it's basically a translation and rotation matrix. The thing here is that our vector, the rotation vector is on a different format, which is called Rodriguez, and this is not what we actually need. We need to convert these R back into a rotation matrix. So this is the main reason why we apply this OpenCV method, which is cv2.rodriguez, and inputs the R vector that it's directly returned by solvePnP. And once that we got the rotation matrix, we can the rotation matrix and the translation matrix, we can literally initialize this in order to build a transformation matrix, which is this, and we have already declared this into our constructor, which is literally an identity matrix 4x4. This is what it actually means. It's only initialized, and then we're gonna fill this empty matrix with our vectors that have been extracted by solvePnP. This is what these 2 lines does. And then we're going to create our homogeneous coordinates for our world landmarks array. And this is what it's actually doing. We're concatenating the world landmarks array with another column filled with ones. And this is basically for creating the homogeneous coordinates. And finally, we're going to apply this transformation into our homogeneous coordinates. And basically, using this symbol to multiply this matrix. There were points home, which means that they are already homogeneous coordinates, with our transformation matrix, which already includes our rotation and translation vector, which is literally the same process that I've written here. solvePnP returns rotation and Rodriguez format. We need to transform into rotation matrix, now our big. I will then literally build the homogeneous transformation matrix, which the transformation literally includes the rotation, translation, and homogeneous coordinates. And this is what we got from the transformation. At the end, we only have to do it's to apply the transformation, and don't forget to actually use the transpose from the matrix in order to follow the NumPy arrays convention. So this is the main reason why we use the transpose. And at the end, when I was plotting the output, I realized that the y-axis was actually inverted. So this is why every y coordinate is multiplied by -1, so we can get the output that we expected. And here's basically the function to plot the result. As I said before, we're using the list of lists declared on the constructor in order to plot it into an easier way. So instead of plotting every single part of the landmarks, we're plotting different arrays. For example, first a complete arm is plotted, then the second one, then the head, the chest, etc. But everything is plotted at the same time on real time. So it's pretty basic. It's pretty basic. So as you can see, there's nothing special. It's just about how to actually apply this concept into a real world situation. And I think that's the main advantage of this process. As we saw before, these are our landmarks that are printed by our algorithm. And again, let's check what we got. And it actually changes in real time. So this is our first, the first thing that we should do for our system. And in the future, we'll be posting a video about how to actually transfer these landmarks into our avatar, which will be built with Unity. The final product expected to be working with ROS2. This transmission of landmarks will be transmitted with ROS2 into Unity. So this is expected to be our final result. On the next video, we'll be working with implementing these landmarks into Unity. But you have to take into account different things before working. I was trying to test different methods to how to work with this 3D coordinates into Unity. And one thing that I realized is that you cannot work directly to retarget these landmarks directly into a bone of the rig of your avatar. Why? Because if you assign directly a coordinate to a bone, it literally collapses. It doesn't work. So just you have to be real careful when doing this process of retargeting. So for this case, we're going to work with some kind of inverse kinematics. Well, it's not actually an inverse kinematics process. It's something kind of similar, but it can't be related with this process. But I mean, it's basically working with quaternions and local rotations for every single bone of the rig. But the inputs of this rotation, it's basically this landmarks from MediaPipe, global landmarks. So this is just the beginning of the process. So I hope that you could understand a little bit about these different concepts that are really, really useful in computer vision algorithms. So I hope you enjoyed the video, guys. If you have any doubt or any question, just let me know here in the comment section below. I'll be trying to answer it. If not, you can send me a message, direct message, and I'll be trying to answer as fast as possible if you have any particular doubt or anything related to the project. So again, thanks for watching, and we'll be working in the future. So see you guys. Thank you.